Welcome everybody. My name is Jesus. I'm an aerospace engineer with a master in astronautics from Cranfield University, and I'm a collaborator at Orbital EOS, where we apply Earth observation for oil spill monitoring in the oceans. And we also do a lot of things, but that's our main field. Welcome everybody from all around the world, the 5 continents, people from America, people from Africa, Europe, Asia. I think that from Oceania there is also some people. And let's begin. There it is. Okay. I'm gonna share my screen. Can you guys see my screen?
Yeah, we do.
Okay, perfect. Thank you very much. Okay, here we go. Here a little introduction of the corporative presentation. We're going to talk about everything you need to know about satellites, space missions, satellites, what are satellites about, what do you need to understand? Like, I want to break that mystery of what satellites are. Like, it's a black box and it looks at Earth. Well, I'm going to show you that we're going to go piece by piece in a satellite to understand it, okay? If you have any questions, please wait until the end. Oh, someone is drawing. Please stop doing that. Thank you. If you have any questions, please wait until the end. And in the end, we will answer every question. If at some point you have to leave the webinar, don't worry, it's going to be recorded, and I will send it personally to your email with a attendance certificate from the company. Okay. First, to begin, I want to make you think a little bit and show you a very beautiful image from Earth, from orbit. We can see here Italy, for example. And I want to cite some relevant person in the history of humankind who was Yuri Gagarin, the first person to go to low Earth's orbit, to leave the surface of Earth, the atmosphere. The Earth is blue. The first thing he said through the radio was, "The Earth is blue. It is amazing." That happened in 1961, and it's an effect. It's a reaction that all the people that see Earth from space feel, and I think that we can have the same feeling without having to go there. But there are so many tools that allow us to see from the International Space Station what we can view on Earth. It's a reflection, like to the blue marble that it's called. Also, I would like to ask you some questions before we begin, to know where we are at. Like, why do we use satellites? If you please could answer in the chat, why do we use satellites? Why aren't we using anything else? Yes, a short couple words, please. Like communications, okay, gather data, navigation, monitoring, communications, weather, big data, GPS. Very well, very well. That answers the question of what for, okay? But I want you to think, why do we use satellites? Further point of view, okay? Anything else? Why don't we use, I don't know, planes or platforms, towers, spying, okay? Fastest way to travel around the globe, exploring. And what benefits do we have from satellites that we don't have in anything else? Okay, satellites don't get shut down, simplify life. No details. Okay, I hope that by the end of the webinar, we can all answer perfectly these questions. But there is a tendency through the years that the technology has developed, and we have been able to build bigger and bigger satellites. We have been able to make stronger structure, bigger solar panels, and also we have made bigger rockets that can take bigger payloads to orbit. You can see here telecommunication satellites, Intelsat, how through 40, 50 years, they have kept growing. Apart from that growing, well, here we have an image of the satellite, Intelsat, the massive, the biggest Intelsat satellite. Here we can see the long things are the solar panels, the circle things are the antenna. This is its size compared to a Tesla Model S. And here's its size compared to a Airbus A320 to think about how big a satellite can become. Here we have a picture of the Intelsat 29E. Please, I don't know if you could please mute yourself. Thank you very much. Of course, this is not deployed at launch. This is in a very little capsule, and then it opens when it's in orbit. But just to have a measurement of how big it can become. I was saying, apart from that, also satellites are becoming smaller. Same thing as with a computer. You know, the technology becomes more and more efficient. We have better solar panels, better batteries, better computers, better cameras. And here are the different classifications of satellites. Yeah, terminology mainly. Mini satellites, microsatellites, nanosatellites, picosatellites, and CubeSats. CubeSats can be considered between different other categories, and a CubeSat is a standardized measure that we're going to explain now that has disrupted the status quo of the satellite industry. This is a CubeSat. This is the size of CubeSat. It fits in a hand. This is a 1 unit CubeSat. It's a standardized measure of 10 centimeters by 10 centimeters by 10 centimeters and about 1.3 kilograms, 2.9 pounds. And it was designed in 1999 by these two brilliant men, Jordi Puig and Bob Twiggs, in California, from the California Polytechnic State Institute and Stanford University. And they came out with this 21 years ago. Also in Stanford happened the femtosats developed by Zach Manchester in the Kicksat project, and they're even smaller. You can see it fits in a hand, and it's a tiny satellite with, like, you can see a couple of antennas, a little solar panel, a little CPU, and this is what the CubeSat meant is the democratization of space became easier, like easier for universities, for institutions, for organizations to build a satellite, not only big corporations or agencies. And this femtosat could represent that too, you know, that maybe for a couple of $100 or a couple thousand, you could buy these little experiments that could be deployed in orbit. Here we see some graphs that represent the tendencies of the missions that have been sent to space. We see here in geosynchronous orbit. That's an orbit that it's synchronized with Earth, and that's an orbit of 24 hours. We see how they become bigger. These are mainly telecommunication satellites. This means more antennas. Lower orbit, they become smaller as they are so close that we don't need that same. It's not used for the same infrastructure. And in the tendency of all the spacecraft missions is it's decreasing. And we see also a graph of how through the years the lifetime of the satellites have increased. That means that more years equals less money, because you have to buy and build the satellites, how the power of the satellites have increased too. And that means more instruments, more payload, and how the mass in general here has increased a little. And who pays for this? You know, like where does the money come from? Well, there are different corporations that work on satellites. There are civil organizations that can be rather national or international, like, for example, the Italian Space Agency, the Japanese Space Agency, the European Space Agency. and they are mainly working on science, on research, but also geolocation networks like Galileo is. There are also military motivations that can be rather national. For example, let's say the French government, or international, if it would be for NATO, for example, other international military organization. They can be used for like surveillance or GPS, which was created as a military instrument. There are also commercial missions, like they could be from telecommunications or TV, or I want to observe this region of the world, and a private company built the satellite, or just to build the satellite. So the space mission, what is a space mission? There are multiple elements, like the space segment, which is the satellite in orbit operating, but it's also the application of the data that the satellite collects, the orbit that the satellite is traveling through, the launch, the putting in orbit of such satellite, the ground segment that communicates with the satellite, and the operations of the satellite. You will have to change the orientations or the solar panels, or look at certain point on the surface of Earth. I would like you to put in the chat now, what can we find in a spacecraft? Like, what do you think that we can see? What elements? Like, I don't know, maybe we can find something to generate energy, or could you please put it in the chat so we interact a little, like it's not only me talking? Or maybe something, I don't know, a sandwich maker. Can we find that in a spacecraft? Yes, no? Else? Pulsion, telecom, power supply, sensor, antenna. That's all correct. Yeah, very well, guys. Propulsion system, GPS, solar panels. Very well, guys. Yeah. Oh, there is enough level here. Like people know what they are talking about. Well, let's see what we can find in a spacecraft. This is a representation that's gonna go with us for the rest of the presentation. Okay, that I found it online. It's very cool, and we're gonna unveil the interior of this spacecraft and go step by step what we can. First is the payload, which is the primal motivation of the whole mission. Why do we put something in orbit? It's because we need something else. Rather, it's a telescope, a big antenna, anything, an experiment, a physical experiment that we want to do at a certain atmospheric height, or with certain conditions of temperature. This is the motivation of mission payload. Then it's the structure, what makes the chassis that brings everything together and makes sure that the satellite is stable, that while we are building it, also it doesn't tear apart, and that it doesn't have any deformation because of temperature or oxidation. It's a key part. It's like the skeleton of the satellite. It's important is the very first assembly, since we do the test that, for example, the vibration test, the transportation from one place to another to put some instruments while building, while it's in orbit, it should also be stable, and of course during launch. I'm going to show you now a link to a web page from Ariane program. And I'm going to show you different elements. We're going to go quickly through the elements of a rocket, of a launcher, and where the satellite is located and everything. Okay. Well, here we see where the payload is on top here, and to put together the different stages of rockets, we use these rings. Okay, the adapters, that it makes the more efficient way to propose satellites possible. That is, do not have a very big rocket with one engine, but have little engines, like for example here we can see, and we propulse, and when we run out of fuel, we go to the next stage. Here is another stage, another ring like that. Those are built, for example, in Spain for the European program. Here we see another engine, when they are building it like if it was a Lego. We see the cryogenic main state where all the fuel, like the liquid fuel, is stored at very low temperatures. The solid rocket boosters that go beside the rocket to help it propulse and help it fight against gravity. And of course, the engine, the main engine that uses the cryogenic fuel that we have talked about. That's everything. Now we're going back to the presentation. We're going to see here now a quick launch, okay, from Ariane 6 from French Guiana to see what the satellite has to go through. It has to be able to survive all of this and arrive to orbit properly in one piece. There's the ignition. And it's wonderful to see. I think that nobody can see it and do not react to it. I think it's just amazing to see. And there is a very fragile satellite and payload, and it has to survive this. So it's key that we have a strong satellite, and that it survives, and we test it, and we make sure that everything will keep working after this. Well, we are going to continue, but this is not only the way to put satellites in orbit. This is a very expensive way to put 1 or 2 satellites per launch, and there are other systems. Like for example, in the right we have the Soyuz system that used by the Roscosmos agency, where we see multiple satellites. We see like 4 here, well 6, the ones behind 2. But we can also deploy satellites from the International Space Station here, for example, with the NanoRack that deploys CubeSat, and we don't need a very big launch to put the little CubeSat in. We need something that has to go to the ISS, but it's another different way to put this in orbit. Next, the electrical power system. Okay, here we see the animation, and it's integrated by multiple parts, like everybody knows the solar arrays that are used on Earth too, the electric batteries that store the energy, and this energy is distributed to like the payload, the systems, the computers. We have to make sure that while there is an eclipse, we keep having energy. For example, in this orbit here, we have sun, but during darkness, we have to make sure that the batteries work and that the satellite keeps functioning. Primary source, solar; secondary, battery. Here we have the International Space Station, which is an in-orbit laboratory, and these are the solar panels of the International Space Station, and they are very big, they are massive, and they produce all the energy required for it to function. Here I'm going to give you some comparison between daily life things we can have and how much power they require. Okay, in orbit we can produce from 5 to 100,000 watts of energy. We can also have radioisotope reactors, nuclear reactors that produce maybe different fission reactions and produce energy, or maybe by the decay of the reactive material it produces energy. We can also have fuel cells like Endeavor, and this is just burning fuel and produces energy. Here is the power that some things need. For example, a computer, 45 watts, a washing machine, 1,500. Satellites, this is one of the Sentinel satellites, 5,900. And the International Space Station is able to produce 100,000 watts of electricity with its solar panels. The electrical system is very connected to the mechanical system, because as we said before, the solar panels cannot be deployed at launch, so they have to be retracted, and then when we are in orbit, we open it, like we can see in the upper one, like this circle scene, or this small CubeSat, or this other solar panel that it's like a blind from a house, and it rolls away, and this allows to have a surface of solar energy bigger than the surface of the satellite. This is a graph that shows the different efficiencies of batteries through history, and we can see how the tendency is to improve. You know, we have more and more and better batteries through time. This is also the temperature range that some instruments work on, like the lithium cells, like the batteries. We have to make sure that it's not gets that doesn't get too cold, because it would stop working. Also the propulsion system, the structures. We have to make sure that all this is tested on Earth before we launch it to space. That connects us to the thermal subsystem, that makes sure that those temperatures are followed. And I'm gonna show you what are the thermal subsystems, the radiators of the International Space Station, which are, we knew the solar panels, but the radiators are these big white things, and this emits energy so that the station doesn't get too hot. We have to find a thermal balance between all the parts of the satellite and make sure that what part doesn't get deformation, that it doesn't get burned because of the atmosphere, or this part gets hot and this part gets cold, and maybe a computer is not working properly. And to use that, you can use rather radiators, or a finishing of the surface, or use the shadow with the sun. For example, we can see that one thing that is similar to Earth, that things get burned in space. You know, it's not a vacuum and no temperature or anything. No, things can deteriorate, and we have to take that into account too. Because if things deform, it can happen the process of outgassing, which is that the inner pressure of the satellite interacts with the vacuum of the space, and things wrong can happen, like maybe some conduction, some tubes break, or the cryogenic or the fuel breaks apart and goes to a place it shouldn't be. So we have to take care of that. Can also use the energy of the sun to regulate temperature. The side where the sun is heating will be much hotter than the side that it's in the shade, and we have to play with that in a satellite. And also take into account the energy that comes from Earth, you know, because the sun goes to Earth, the sun goes to the satellite, but Earth also emits infrared radiation. These are the surfaces that we can use to isolate the satellite, or radiators like we can find on a car or on a motorbike. We can also have a system of like a very, very cold fluid for such thing. From this, we are going to the propulsion system that some people talk about it before. And there are multiple elements for the propulsion system, like the engine, the tank, the plumbing. And we're going to see what we would use the propulsion system for. There is a very big subsystem, very important in a space mission, which is the attitude and control, and it's separated into two subsystems: attitude determination and control, and guidance navigation and control. The first one is about the orientation, the positioning. Where is the satellite looking at? Like if we want to see that it's an antenna, it should be facing Earth. If it's a telescope pointing at, I don't know, Saturn. And the other one, guidance navigation, is where it's in the orbit, what inclination, is it going through the right place, is it connecting because it's passing at the right time. And for such thing, for keeping that orbit and keeping that stability, there are some systems, like for example, passive, that it means that it doesn't require energy, or that much energy, like gravitational gradient, or we have a heavier part of the satellite that's gonna go down, like just like a pendulum, you know. And we can also have a magnetic control that is synchronizes with the magnetic field of Earth. We can also have active forms, like for example, this one, where reaction wheels are used. This is a real video. It's not fake or anything. These reaction wheels rotate to generate momentum, and this momentum keeps the satellite stable. From this, we go to the communication subsystem, and what this uses, what this implies, is that we need to communicate with satellite to know where it is, to know how it's doing. Like, are you okay? Do you need? Do you have enough energy? Do you have enough information? And it's connected to Earth at almost every moment, to one station, to two stations. It can also connect maybe to other satellites and communicate between each other. And we have to take into account that this communication has to get through the atmosphere, through the ionosphere, go through the vacuum of space, and we have to prepare all that technology to work. The communication that it usually uses is a 2 gigahertz frequency. The S-band communicates with satellites. And the ground segment that communicates with the satellite, they have very big antennas that point at the satellite to receive the information and everything. We can see here in the lower right, the ground control center in NASA. I think this is when the InSight mission landed on Mars, and they are very happy because they communicated with the satellite and they saw that it landed properly. It's also, we receive energy that said, hey, the satellite is saying, hey, I'm okay, everything is fine, I have energy, I have information, but we can also order it to do things. Hey, point at this thing, do this other thing. And after we have that information, we can also like read it. Okay, what does it say? Are the instruments of the payload working properly? There are some images of the telecommunication networks on Earth. On the left is the NASA one, and on the right is the European Space Agency one. You can see that there are all around the world, so there is always communication with satellite. Doesn't matter in which position of the orbit it is. And on the right upper part, we can see the size of the antennas and the weight of the antennas that we put in orbit. You know, like it just they are very light. You know, we don't need that much weight. The less weight we put in the antennas, the more weight we can put in the payload. And now the data handling system, which it's the internal system that handles all the information that the satellite has, like knowing the position and everything. And the computers that are used are very robust, but very basic. In your smartphone, you probably have a much powerful computers than in these satellites. And they are expensive, though they are very expensive, but you can see that the requirements of power can be very low, very low, compared to the 45 watts that we had before. And here we can see an example, like in a simulation mission, of how much data it could produce. Yeah, we're talking about megabits, you know, like probably a song that you download from Spotify, it's heavier than mass spectrometer, imager, particle detector, magnetometer of a full functional satellite mission. And on the left, we can see, for example, a computer from a CubeSat. Now, what I would like to talk is about things don't always go right, and mistakes happen because we are human, and mainly this happens by human mistakes, of software mistakes. They have been applied by humans too, though. For example, on the lower left one, I'm going to talk about the Mars Orbiter mission sent by NASA, that it was programmed, the software was programmed in kilometers in the metric system, but the machine was designed in miles. So things did not work. And when it was approaching Mars, they saw that the trajectory was not the correct one, and I was diverting, and it crashed against Mars surface, and $200 million disappeared. It's expensive fireworks on the Mars surface. Also, in the upper right, we see the Antarctic. There was a satellite that was sent to pass over Antarctica and monitor the ozone layer. But like the value, the emptiness, the hole in the ozone layer was so big, the computer was not able to read it, because the range of values that it was set to was too small. And they thought, okay, the atmosphere holds probably between these, but the hole was here, the absence of ozone. Until they found out that, they thought the mission was not operating properly. The last one, the Phobos 2 mission that was sent to one of the moons of natural satellites of Mars by the USSR in 1989. In a software update, same way you update your Android or your iOS. They updated their software on orbit, and what happened is that they made a mistake. There was a bug on the software, and because of that, the orbit changed. And we're talking about a moon that it's 30 kilometers wide and it's biggest, so you have to be very precise. And because of that, it went to another orbit and never arrived to the destination. I'm also going to show you a launch here of Ariane 6, Ariane 5. We saw a successful launch, but this was the very first launch in 1996. Okay, let's see what happened. Okay, everything is going fine, going up, going up. The whole world expecting this. At least the first time they launched the European launcher. Okay, going up. But it crashed, it exploded. 37 seconds lasted that flight. And what happened is that the software, for some reason, thought that the launcher was in horizontal instead of vertical. There was a 90-degree mistake, and so it was trying to rotate, and that made the rocket crash. And this shows that mistakes can happen. Like I'm gonna show you now the poor guy that was in command of this, how you handle the situation about after years of research. And look at the poor guy. He it's sad that these mistakes happen, but the learning from these mistakes is that we have to be careful, and we have to accept the mistakes, learn from them, and make the next mission successful. Right now, they have made very successful with the Ariane 5 mission. They are very promising. Not regarding ones of the last days, but they're good. What we can learn is that software is very important, guys. That was everything. Thank you very much for coming here today. And if you have any questions,